Okay, we're going to use those intermolecular ideas from last unit section to talk about different properties of solids. So we talked about, you had ionic compounds, and they're held together very strongly, very big Coulombic attraction, and they form these lattice structures. And so we're not going to get into it in this class, but you could take material science classes in the future, and you could talk about the X-ray diffraction techniques that are used to try to figure out the geometries and the arrangement of all those lattice structures. All we need to know about these crystal lattice structures for ionic compounds is general ideas like high melting point, high boiling point. Since they have such a high boiling point, they have virtually no vapor pressure. They have high lattice energy. I guess because they have high lattice energy, they have those different properties. And that's that strong Coulombic attraction between the cation and the anion. If they're in that lattice structure form, they don't conduct electricity. But if you were able to put those into water and they dissolve in water and become mobile ions, then it can conduct electricity. This is about as far as we're going to get with these X-ray diffraction techniques, just kind of related to maybe some classes you've had previously in bio. Watson and Crick credited with the structure of DNA. Well, without Rosalind Franklin and her X-ray diffraction, I don't know if that would have been possible for them, or at least not in that time frame. Okay, so again, I've shown this picture before. A lattice is a repeating structure. In this case, cations aligned with anions, so forth, so forth, so forth. But there's other types of structures that are solids that are still crystalline, and one of them is called a covalent network solid, or covalent network crystal. And so covalent means covalent bonds. So it can't be one of those ionic crystals like we had before. And there's a lot of different types of covalent network crystals. I took a picture of just a couple here. Diamonds are repeating structures of carbon, repeating a lattice of carbons, covalently bonded to each other. And that's going to be the one here on the left. That is diamonds, and that's its structure. It's hard to see a lot in there, but almost every opportunity for the carbon to be bonded in an sp3 hybridization, it occurs. Now, obviously, on the outsides, that's not going to happen, but anywhere in towards the middle of the crystal, that's going to occur. And then with graphite, still all carbons, but the hybridization there is generally going to be sp2 hybridization. So, here's your carbon with more carbons, and then with graphite, it's going to be more like that look. And that gives it certain types of properties. So diamonds are very, very, very strong, very brittle. Graphite, on the other hand, because of this orientation here, this sp2 hybridization, they end up forming these sheets. And these sheets are well connected inside that sheet. The carbons are well connected there with this sp2 bonding, but sheet to sheet to sheet, there is no covalent bonding that occurs between these sheets. The only bonding that can occur is more like a Lund dispersal force, not very strong. So that gives it much different properties than diamonds. So if you take your graphite pencil and you if you draw it across a piece of paper, those sheets are going to come off easily from each other off the tip of your pencil. And here's another one, silicone dioxide, and there's some other ones too, but they are covalently bonded together, so that will give it a high melting point, high boiling point. You know, depending on what the material is, obviously it's going to have a different number. They're generally hard, they're generally rigid. Yes, there's going to be a lot of variation in that. Obviously, diamonds and graphite are very different from each other. There's some other solids, and these solids don't really have the same properties of the last solids, and they're called molecular crystals. And they're not held together with ionic or covalent bonds. They're held together by intermolecular forces. So carbon dioxide, we talked about, you could have dry ice, a solid, but very low melting points, very low boiling points. What's going to happen with dry ice, if you just let it out, it's going to sublime, go directly from a solid back to a gas. And why? Because it doesn't have very strong intermolecular forces. What kind of intermolecular forces does it have? LD forces. There are other molecules here that can form these crystals, and yes, they could have more than just LD forces, but they might have some dipole in case of SO2. That is a dipole. It has a dipole because it has some asymmetry to it. So it might have a different melting point and boiling point than carbon dioxide. And then obviously sugar is a solid at room temperature, but it's easily melted. So it probably has LD, but it also, you don't have to know the structure of sucrose or glucose. This is sucrose, but I could have put glucose in there too. It has a little bit of hydrogen bonding that also occurs. There's also metallic crystals, and we talked about metallic crystals earlier with alloys, so we won't get very much in detail today about that. But again, I would say most metallic crystals have high melting points, but you know, they vary. They vary for sure. We talked about the sea of delocalized electrons in that conduction band, and that was about the band theory, and that allows it to have some properties like malleability. It's ductile. It can conduct electricity in solid form. And then we have another, we will not go into hardly any detail at all, but amorphous solids, not well defined. When I say that, I mean the atoms or the molecules are not well defined. They don't necessarily stay in their location. Where would you kind of see this occur? If you would look at an old house or maybe an old church and look at one of their old window panes. Newer windows have a lot of coatings that keep this from happening, but that glass, those molecules that are in the glass, with gravity, they kind of spend more time closer to the bottom of the window. So the bottom of the window actually gets a little thicker. The top of the window is a little bit thinner, and that would be a kind of a description, or not a description, but a example of amorphous solids. Yeah, we talked about the sea of electrons before. We talked about the conduction bands before. We even talked about alloys before. So just, I don't know if I gave you this picture or not before, but here would be a pure metal. I don't know, let's call it, let's call it iron. And then if you would insert a few carbons in there, then you wouldn't have just iron. You'd have iron with carbon, and this would make this alloy now stronger, more rigid, and this would be an example of steel. On the other hand, these are not drawn to scale, but let's make this copper and zinc. I think that was the one I gave you guys before. Copper and zinc are very close together as far as size, so I don't know, these different sizes here might be a little too far apart, but you get the idea. So substitutional, you take some of the atoms out, replace it with another atom that's close to the same size. And then interstitial, you just insert smaller atoms in between the spaces that there are no atoms of metal. And in case you were wondering about a bunch of different alloys, none of these are going to be on the test. These are just maybe some things just to be aware of. I think you probably know a little bit about brass. You might know a little bit about bronze. In history, they were significant. Significant enough that there's a bronze age. Cast iron, you might know a little bit about that. What else? Yeah, probably not too much about pewter. White gold, sterling silver. Why do they not make jewelry or other things? Place settings, stuff like that. They don't make that out of pure gold, pure silver. It's too soft. So you have to add some other atoms to it that would give it a little more of a hardness. Obviously, we know about steel, and there's tremendous amount of variation with steel, depending on what you're trying to do. So you might have different types of atoms included there. You might know a tiny bit about solder. So there you go. By the way, this one, amalgam, is if you know someone probably not in their 20s or teens, but maybe someone in their 50s, 60s, 70s, they may have had cavities in their teeth, and the fillings that they may have had to repair that might be an amalgam. It has, interesting, it has mercury in it. I think that'll be it for today.